is managed as a continuous system that spans national borders and oceans. The system divides the sky into defined portions of airspace. Each portion is assigned to an authority that provides navigation and traffic services within it. Those assignments follow international standards and local regulations. The result is a layered framework of control that operates at all hours. At the top level, an international body establishes common standards and recommended practices. These standards guide how airspace may be structured and how services should be delivered. National authorities adopt and adapt those standards. They set the legal basis for operations and for the organizations that carry out air traffic management within each country. Airspace is commonly divided into regions called flight information regions. Each region has published boundaries. A responsible organization manages traffic within each region. That organization is often called an air navigation service provider. It may be a civil authority, a dedicated agency, or a commercial entity operating under national oversight. The provider staffs control centers. It maintains equipment. It issues procedures for routes and sectors. Control services operate at different levels. Near airports, aerodrome control manages arriving and departing aircraft on runways and in the immediate vicinity. Terminal control, or approach control, handles aircraft in the terminal area, where climb, descent, and initial routing occur. En route control manages aircraft in the cruise phase as they traverse larger portions of airspace. These levels are coordinated to maintain orderly flow and to ensure separation between aircraft. Sectors divide the operational workload within a region. A sector is a defined volume of airspace with specific altitude limits and lateral boundaries. Controllers are assigned to sectors. They are responsible for the aircraft within their sector. As aircraft move, responsibility is transferred between sectors. Those transfers follow set procedures. They include position reports, radar handoffs, and coordination messages. The handoff is an essential mechanism that keeps control continuous and predictable. Routes form the skeleton of traffic flow. Airways and standard routes link major airports and navigational fixes. Pilots file flight plans that reference these routes. Controllers use route structures to sequence aircraft and to apply separation standards. In oceanic and remote areas, routes are defined to use available navigation and surveillance capabilities. On routes with dense traffic, procedures include spacing rules and speed control so that aircraft maintain safe distances. Separation is the operational principle that prevents conflicts. Separation is achieved laterally, longitudinally, or vertically. Lateral separation places aircraft on different tracks. Longitudinal separation keeps aircraft a fixed distance along the same track. Vertical separation ensures a difference in altitude between aircraft. Standards for separation vary by airspace and by available surveillance. Where precise surveillance is available, separation standards can be reduced. Where surveillance is limited, larger buffers are required. Controllers apply these standards continuously as traffic moves. Surveillance systems provide the position information that supports separation. Primary radar returns the reflected echo of an aircraft. Secondary surveillance gives position and identity information through transponder responses. Satellite-based monitoring and automatic dependent surveillance broadcast have expanded coverage. These systems feed into control center displays and into flight tracking networks. Where surveillance gaps exist, procedural methods such as position reporting over designated points, substitute for continuous tracking. Communications enable instruction and coordination. Voice communication on very high frequency radio connects pilots and controllers in many phases of flight. High-frequency radio serves long-distance communication, especially over oceans. Data link systems carry text-based clearances and position reports. Landline and secure data networks connect control centers to each other and to airline operations units. Coordination messages move along those networks to support traffic flow and to exchange flight information between authorities. Traffic flow management operates alongside tactical control. Flow management plans operations to match demand with available capacity. It includes strategic planning days in advance, pre-tactical adjustments hours before operations, and tactical measures during the day of operations. Slot allocation, ground delay programs, and rerouting are tools used to prevent congestion and excessive delays in the air and on the ground. Flow management centers analyze forecast demand and sector capacity. They issue measures to smooth peaks and to prioritize traffic when necessary. International coordination is a continuous requirement. Flights cross borders and jurisdictions. Border crossings trigger coordination between adjacent providers. Agreements define transfer points and procedures for data exchange and handoffs. Regional organizations support harmonization across neighboring states. Common procedures reduce complexity for operators and controllers. They create predictable paths for international flights. Navigation infrastructure underpins the system. Ground-based navigation aids still support many procedures. Satellite navigation allows direct routing and optimized profiles. Instrument procedures govern approaches and departures in reduced visibility. Performance-based navigation enables new route designs and more efficient spacing. Implementation follows a gradual process of certification and training. The result is an evolving mixture of legacy and modern systems operating in parallel. Operational resilience is built into the system. Redundancy exists in communications, surveillance, and data links. Control centers maintain backup systems and contingency plans. Staffing models ensure coverage for shift changes and high-demand periods. Maintenance schedules are planned to minimize disruption. When unexpected events occur, coordinated procedures and established contingency routes maintain continuity of traffic management. The full scope of air traffic systems includes people, procedures, hardware, and software operating together. It covers small regional airports and the busiest international hubs. It spans contingent operations over oceans and dense control sectors over continental airspace. The system functions as a network of linked units that exchange information and apply shared standards. This networked arrangement enables aircraft to move safely and predictably through the global airspace system without interruption. Controlled airspace is organized into layers and corridors. These divisions assign responsibility for monitoring and directing aircraft. The arrangement helps maintain safe distances between aircraft and manages volumes of traffic. The system is based on altitude bands, named routes, and geographic boundaries. Each element is defined on operational charts and in regulatory documents. Flight levels are one way to describe vertical position in the atmosphere. A flight level is an altitude expressed relative to a standard pressure setting. Above a defined transition altitude, aircraft use the standard pressure reference rather than local sea level pressure. This practice makes vertical separation uniform across large areas. Flight levels are often given in hundreds of feet. For example, a flight level noted as FL 350 represents approximately 35,000 feet under the standard pressure setting. Below the transition altitude, altitudes are commonly reported in feet above mean sea level using local pressure settings. This dual system creates a clear boundary for how pilots and controllers describe vertical position. The transition altitude and the transition level vary by country. In some regions, the transition altitude may be relatively low. In other regions, it may be higher. The difference between the transition altitude and the transition level is the transition layer. That layer provides a buffer where aircraft change their pressure reference. The precise values are published so that pilots and controllers operate with the same reference. Air routes form the horizontal structure of controlled airspace. Airways are defined corridors that link navigational fixes, intersections, or waypoints. Historically, many airways aligned with ground-based radio navigation aids. Modern routes increasingly use satellite-based navigation. Airways may be categorized by altitude. Upper airways are intended for higher flight levels, while lower airways serve lower altitudes. Each airway has an identifying code. Along these airways, procedural and radar-based control manages separation and traffic flow. Routes also include oceanic tracks and organized track systems. Over oceans where ground-based navigation is not available, routes are defined by coordinates and waypoints. Oceanic routes often require specific procedures for position reporting and separation. They accommodate long-haul flights between continents and rely on communication and surveillance arrangements adapted to the remote environment. Air route design considers several factors. Terrain and obstacles influence minimum safe altitudes. Traffic patterns and common origins and destinations shape capacity needs. Meteorological patterns and preferred winds affect where high-volume routes are placed. The result is a network of preferred paths that concentrate traffic along efficient tracks. This concentration allows for predictable flows that air traffic management can supervise. Regional boundaries divide responsibility for surveillance and control. Flight information regions, or FIRs, are the principal way that airspace is partitioned. Each FIR has an authority responsible for providing air traffic services within its limits. FIR boundaries are established through international agreements and national regulations. They may follow political borders, geographic features, or arbitrary lines of latitude and longitude. Control centers within FIRs manage traffic inside the region, and they coordinate with neighboring centers where traffic crosses boundaries. Within a large FIR, control responsibility is often further subdivided. Area control centers divide their airspace into sectors. Each sector covers a defined volume of airspace with lateral and vertical limits. Sector boundaries are drawn to balance workload. As traffic levels change, sectors can be combined or split. Controllers work assigned sectors and hand off aircraft to adjacent sectors as flights progress. This subdivision allows for continuous monitoring while keeping individual controller workloads manageable. Terminal control areas around major airports create a different kind of regional boundary. Terminal areas encompass approach and departure procedures and often extend upward to meet en route control. These areas are shaped to manage the concentration of arrivals and departures. They have defined entry and exit points that link terminal control with the en route network. Traffic transitions between these areas follow published procedures and may involve speed and altitude constraints to fit into the broader flow. Airspace classifications influence how traffic is managed within the various regions. Controlled airspace classifications denote the level of air traffic control service available and the rules that apply. For example, some classes require pilots to operate under instrument flight rules and maintain contact with air traffic control. Other classes permit more flexible operations when traffic and visibility conditions allow. The classification system provides a framework that both pilots and controllers use to anticipate expected service levels. Vertical boundaries are as important as horizontal limits. Some regions define control up to a specified flight level. Above that level, another authority may assume responsibility, or the airspace may be designated differently. For instance, a national airspace may extend upward to include upper flight levels, while above that, responsibility may pass to a regional or international organization. Vertical limits are published so that operators know which rules and services apply at each altitude. Coordination at boundaries relies on agreed procedures. Handover protocols specify when and how a flight is transferred between controllers. Time-based or position-based transfer points reduce ambiguity. Coordination also covers contingency arrangements, such as when an unexpected weather event or equipment outage requires temporary reallocation of sector boundaries. Published agreements and real-time coordination maintain continuity of service across different control units. Traffic flow management applies across the network of routes and regions. Air traffic control units use planning tools to balance demand and capacity. Flow measures include assigning entry times, adjusting speeds, and routing around constrained areas. These measures aim to maintain orderly movement through the network. They are implemented through clear procedures and communication between affected control units. Information systems support the structure of controlled airspace. Aeronautical information publications contain the formal definitions of boundaries, routes, and operational procedures. Radar and surveillance displays present the positional data that controllers use within the defined sectors. Flight planning systems reference the route network and the applicable regional controls when generating clearances and filing flight plans. Overall, the structure of controlled airspace combines vertical stratification, named routes, and regional divisions. Flight levels standardize vertical references. Airways concentrate traffic along predictable lines. Regional boundaries assign responsibility and manage interactions between different control authorities. Together, these elements form a coordinated framework for guiding aircraft through the shared volume of air. Air traffic control centers manage the flow of aircraft through defined volumes of airspace. Each center has a specific role. Some centers handle the area close to an airport. Others manage aircraft between airports over longer distances. The primary functions are surveillance, coordination, and separation. Each function is distinct. Each function supports the others. Surveillance provides the information that controllers use. Surveillance includes several technologies. Primary radar transmits a radio pulse and listens for echoes. It shows the presence and approximate position of an object. Secondary surveillance uses a transponder aboard an aircraft. The ground station interrogates the transponder. The transponder replies with an identification code and, in many systems, altitude. This combination of primary and secondary radar is common near busy airports and within continental airspace. Automatic Dependent Surveillance, broadcast or ADS-B, is a more recent addition. Aircraft equipped with ADS-B determine their own position using satellite navigation. They broadcast that position periodically. Ground stations and other aircraft can receive these broadcasts. ADS-B provides precise position and velocity information when available. In areas without ground infrastructure, satellites can collect ADS-B signals. Multilateration systems estimate position by measuring differences in signal arrival times at several receivers. These systems complement radar and ADS-B. Surveillance data feeds visual displays and digital processors in control centers. Consoles present aircraft positions on screens. Track labels provide identifiers, altitude, and speed. Flight plan data links to the surveillance picture. Controllers compare predicted trajectories against observed positions. This comparison helps detect potential conflicts between aircraft. Coordination refers to how centers and controllers pass responsibility for an aircraft. Airspace is divided into sectors that are assigned to individual controllers or teams. When an aircraft moves from one sector to another, control responsibility is handed off. Handoffs occur between tower and approach units, between approach and en route centers, and between adjacent en route sectors. The handoff process includes transferring the aircraft's identification, its current flight plan or clearance, and any outstanding instructions. Communication methods include voice radio and data link. Voice remains the primary method in most situations. Controllers use assigned radio frequencies to issue clearances and instructions. Data link systems can transmit clearances and position reports electronically. Flight plan information is exchanged through centralized databases. Digital coordination messages can reduce the need for repeated verbal exchanges. Both voice and data link rely on common phraseology and standardized procedures. This consistency reduces ambiguity during transfers of control. Coordination also involves planning. Controllers use tools to project aircraft trajectories. These tools use surveillance data, flight plans, and performance models. Predicted paths allow controllers to identify potential conflicts early. Tactical adjustments follow, such as assigning different altitudes, headings, or speeds. These adjustments are coordinated with adjacent sectors and with aircraft crews. When traffic density increases, planning horizons extend and coordination becomes more proactive. Separation is the formal method by which controllers ensure that aircraft maintain acceptable distances from each other. Separation can be vertical. Vertical separation uses altitude differences to keep aircraft apart. Aircraft fly at assigned flight levels or altitudes. When vertical separation is available and sufficient, aircraft can cross the same horizontal area at different heights without conflict. Separation can be lateral. Lateral separation uses horizontal distance or different routes. Airways, tracks, and navigation fixes provide structured paths. Controllers assign routes or vectors to achieve lateral spacing. Lateral separation works when navigation accuracy and surveillance coverage support the required margins. Separation can also be longitudinal. Longitudinal separation uses spacing along the same route. It is frequently expressed as a time interval or distance between aircraft. Controllers adjust speeds, or issue sequencing instructions to maintain longitudinal intervals. Longitudinal separation is common on final approach paths and in en route streams of traffic. The method chosen depends on surveillance capability, airspace classification, and traffic conditions. Radar-based separation uses live position information. Procedural separation relies on position reports and navigation estimates when radar coverage is limited or absent. Oceanic control often uses procedural methods. In these areas, controllers use position reports, estimated times over waypoints, and agreed procedures to maintain separation. Automation systems assist in separation management. Conflict alert tools analyze trajectories and identify potential infringements of separation standards. These tools provide alerts at varying lead times. Controllers assess alerts and issue corrective clearances when needed. Flight data processors integrate flight plans with surveillance tracks. Strip boards, in electronic form or paper form depending on the facility, record clearances, coordination notes, and constraints. These records support the sequence of actions that maintain orderly flow. Air traffic flow management operates alongside control centers. It adjusts scheduled departures, reroutes traffic, and imposes ground delays to prevent congestion in the air. Coordination between flow managers and control centers reduces the need for tactical interventions. Flow measures aim to keep traffic within the manageable capacity of affected sectors and airports. Different centers handle different phases of flight. Airport towers manage runway operations and immediate airspace around an airport. Approach and departure units handle arrivals and departures in the surrounding terminal area. Area control centers, sometimes called en route centers, manage aircraft cruising between terminal areas. Oceanic centers manage flights over remote oceanic airspace where radar coverage is minimal. Each center applies surveillance, coordination, and separation methods suited to its environment. Staffing and rostering are part of operational resilience. Controllers work in teams and rotate through positions. Handover between shifts includes briefing on traffic, weather, and equipment status. This continuity supports consistent application of procedures. Technical systems undergo maintenance and redundancy checks. Backup communication and surveillance paths exist to mitigate single-point failures. Training and standardization support consistent operations. Controllers follow national and international regulations. Procedures for handoffs, phraseology, and separation standards are documented. Regular proficiency checks, simulations, and assessments maintain operational competence. Coordination with adjacent national or regional units follows written agreements and letters of arrangement. These documents define transfer points, communication methods, and contingency options. Data sharing and interoperability have increased. Common data formats, standardized surveillance protocols, and agreed coordination procedures allow diverse systems to work together. This interoperability supports smoother handoffs and clearer situational awareness across jurisdictions. In summary, control centers use surveillance systems to observe aircraft. They coordinate actions across sectors and facilities. They apply separation methods to maintain spacing between aircraft. Surveillance, coordination, and separation operate together as a set of technical and procedural practices. These practices organize air traffic flow within and between control centers. Radar and satellite systems provide primary means for determining aircraft positions over large areas. These systems operate in parallel and in combination. They supply positional information to air traffic services, airline operations centers, and automated processing systems. The methods differ in technology, coverage, update rate, and the type of information provided. Together, they form a layered surveillance architecture. Primary radar emits radio pulses and listens for reflections. An antenna transmits short bursts of energy. Those pulses travel outward and reflect off solid objects, including aircraft. Returned echoes are detected and converted into range and bearing measurements. Range is the distance from the radar site to the reflecting object. Bearing is the angle relative to the antenna reference. Primary radar does not depend on any equipment aboard the aircraft. It identifies objects through reflected signals alone. Secondary surveillance radar uses transponders carried by aircraft. The ground station sends an interrogation signal. A transponder aboard the aircraft receives that interrogation and replies. The reply includes a transponder code and, in modern transponders, additional data. Secondary surveillance provides discrete identification and altitude information when the aircraft's transponder supports it. Common transponder modes include Mode A, Mode C, and Mode S. Mode A reports a 4-digit code assigned by controllers. Mode C supplies pressure altitude. Mode S supports selective interrogation and facilitates data link capabilities. Automatic Dependent Surveillance Broadcast, or ADS-B, is a newer surveillance method. ADS-B relies on the aircraft's onboard navigation system, typically GPS, to determine position. The aircraft broadcasts its position and other data at regular intervals. Ground stations, satellites, and other aircraft can receive these broadcasts. Two main variants are ADS-B out and ADS-B in. ADS-B out is the periodic broadcast of the aircraft's state. ADS-B in refers to reception of others' broadcasts by an aircraft or facility. ADS-B messages include position, velocity, identification, and integrity indicators. They allow passive surveillance without interrogation. Satellite-based ADS-B extends coverage beyond ground station limits. Low Earth orbit. Satellite constellations receive ADS-B out transmissions from aircraft. Those satellites relay the messages to ground processing centers. This approach provides surveillance over oceanic and remote areas where ground radars are absent. Geostationary satellites can support data relay and other services, but most space-based ADS-B uses LEO platforms for reduced latency and improved reception geometry. Radar coverage is constrained by line-of-sight limitations. The curvature of the Earth limits how far a radar beam can travel at low altitudes. High-altitude aircraft are visible at greater distances. Low-altitude flights, terrain, and atmospheric conditions can block or degrade radar returns. Secondary surveillance shares similar line-of-sight constraints, since it also relies on radio propagation between ground station and aircraft transponder. Multilateration systems address some of these constraints by using multiple receivers to determine position based on time differences of arrival from a transponder's replies. Surveillance performance is expressed in terms of accuracy, integrity, continuity, and availability. Accuracy describes how close the reported position is to the true position. Integrity refers to confidence that the reported position is correct within specified limits. Continuity is the ability to provide surveillance without interruption. Availability is the proportion of time that the surveillance service can be relied upon. Different systems offer different profiles for these parameters. Primary radar provides independent ranging but lower positional precision. ADS-B provides high positional accuracy when GNSS signals are available. Signal environment affects radar performance. Ground clutter, or echoes from terrain and structures, appears on primary radar displays. Weather phenomena, such as heavy precipitation, can attenuate radar signals and produce false returns. Secondary surveillance can be affected by signal masking and transponder malfunctions. ADS-B performance depends on the integrity of satellite navigation and the aircraft's broadcast systems. Processors monitor signal quality and apply filters to detect inconsistent or corrupted data. Surveillance data requires processing before it becomes useful for traffic management. Raw returns and received broadcasts are ingested by surveillance processors. These systems correlate successive observations to form tracks. Correlation links discrete detections that belong to the same object over time. Tracking algorithms predict motion and update tracks with new observations. Prediction allows systems to estimate positions between updates and to smooth measurement noise. Many systems use standard estimation techniques to optimize these functions and to provide stable, continuous tracks. Identification of targets combines surveillance and flight plan information. Mode A codes, call signs in Mode S transmissions, and ADS-B identification fields link observed targets to flight plans. Flight data processing systems perform correlation between filed flight plans and observed tracks. When a match is made, the track inherits the flight plan identification. This supports controller situational awareness and automated conflict detection tools. When identification is missing or ambiguous, procedures exist for controllers to query pilots or apply temporary measures. Oceanic and remote airspace rely on specific surveillance methods adapted to wide areas. Procedural control has been the traditional approach, using position reports and time-based separation. In modern practice, data link services such as ADS-C provide periodic position reports via satellite or HF link. ADS-C or ADS contract establishes an agreement between the aircraft and a ground system for reporting intervals or event-triggered reports. This approach reduces reliance on voice position reporting and improves the timeliness of position data in remote airspace. International standards govern surveillance message formats and distribution. Asterix is a commonly used data exchange format for surveillance and radar information. ICAO sets requirements and guidance for surveillance performance and procedures. Regional organizations coordinate implementation to ensure interoperability across borders. Surveillance data is distributed to multiple stakeholders, including adjacent control centers and airline operations through dedicated networks and standardized interfaces. Redundancy and fusion improve overall coverage and resilience. Multiple sensors with overlapping coverage feed into fusion engines. Fusion combines data from primary radar, secondary radar, ADS-B, multilateration, and satellite sources. The resulting fused picture leverages the strengths of each source and mitigates individual weaknesses. For example, ADS-B provides high-precision positions, while primary radar offers an independent detection method. Combined use yields a more complete surveillance picture. Latency and update rate are practical considerations. Primary radar rotation rates determine how often a given azimuth is sampled. Secondary surveillance can provide more frequent updates depending on interrogation rates. ADS-B update intervals are defined by the aircraft's transmission rate and system configuration. Satellite relay introduces propagation and processing delays. Surveillance systems account for these timing factors when predicting positions and when presenting information on controller displays. Maintenance and calibration are ongoing aspects of surveillance operations. Radars require periodic alignment, calibration of timing and phase, and verification against known reference targets. Ground stations for ADS-B and multilateration must be monitored for receiver sensitivity and timing synchronization. Satellite-based systems require coordination with space operators for health monitoring and payload performance. Standards and procedures specify checks and monitoring to maintain required performance levels. Surveillance systems evolve with technological advances. Incremental improvements refine accuracy, integrity, and coverage. The combination of ground and space-based assets continues to expand the geographical reach of aircraft monitoring. Systems integration supports consistent tracking across national and oceanic boundaries. The practical effect is a layered, adaptable surveillance architecture that provides positional information across large regions. Flight planning and scheduling systems set the shape of air transport before an aircraft moves from gate to air. They coordinate routes, timings, and resources in advance. These systems combine information about aircraft capabilities, weather, airspace structures, airport capacity, and commercial needs. The process begins weeks or months before a flight and continues through progressive refinement to the moment of departure. Airline scheduling creates a timetable. This timetable lists planned departures and arrivals for a season. It reflects markets, aircraft availability, crew rosters, and ground handling capacity. Timetables respond to demand patterns, regulatory constraints, and airport slot allocations. A slot is a permission to use a runway at a particular time. Slots are allocated at busy airports to limit congestion. Slot allocation systems balance application rules, historical rights, and current operational constraints. They are part of the scheduling framework and influence route timing and aircraft assignments. Route planning uses the network of airways and direct routes available through controlled airspace. Airspace is divided into regions called Flight Information Regions, or FIRs. Each FIR has its own air traffic service providers and route structures. Planners choose routes that align with these structures. Over oceanic and remote areas, structured track systems may apply. An example is a set of daily organized tracks. These tracks change with prevailing winds and are published in advance. Selecting a route involves trade-offs among distance, winds, airspace charges, and traffic complexity. Flight plans capture the planned route and the associated parameters. A flight plan includes departure and destination points, the planned route, cruise altitude, planned speeds, estimated times en route, and fuel allowances. It records any operational constraints such as overflight permits. The format for filing flight plans follows international standards established by aviation authorities. Flight plans are filed electronically with the first air traffic service unit that will handle the aircraft. Filing often occurs many hours before departure for long international flights and closer to departure for shorter operations. Weather information is central to planning. Forecasts of wind, temperature, turbulence, icing, and convection influence route selection and fuel planning. Winds at cruising altitude can assist or hinder progress. Planners use wind forecasts to select flight levels and tracks that minimize fuel burn and time. Weather updates are received continuously, and flight plans may be updated to reflect significant changes. Notices to airmen, or NOTAMs, convey temporary changes to airspace, procedures, or airport facilities. NOTAMs are checked during planning and immediately before departure. Aircraft performance and operational limitations shape schedule feasibility. Each aircraft type has specific fuel burn characteristics, climb and descent profiles, and range capabilities. Weight limits at takeoff and landing can affect fuel and payload calculations. Performance considerations also determine the choice of alternate airports in case the destination becomes unavailable. For extended overwater flights, requirements for diversion airports and additional equipment are part of the planning process. Commercial and operational systems work together. Airline operations control centers and flight dispatch departments coordinate schedules and individual flight plans. Dispatchers monitor aircraft positions, traffic flow, and operational constraints. They approve and file flight plans within the regulatory framework. Scheduled maintenance, crew duty times, and connections for passengers and cargo feed into decisions about departure times and aircraft rotations. Hub and spoke networks rely on synchronized banks of arrivals and departures to facilitate connections. These banks concentrate traffic into short periods and require precise timing in planning. Air traffic flow management provides a link between airline plans and airspace capacity. Flow management organizations analyze demand and capacity across regions and airways. They identify potential bottlenecks and apply measures to balance demand with available capacity. These measures can include adjusting departure times, assigning reroutes, or implementing ground delays. Such actions are usually communicated in advance and coordinated among stakeholders. The objective is to maintain an orderly movement of traffic that fits within available resources. Collaborative decision-making, often abbreviated as CDM, is a structured method for information sharing among airlines, airports, and air traffic service providers. CDM processes exchange data about expected times, aircraft statuses, and operational constraints. These exchanges refine predictions of demand at specific airports and airspace sectors. Improved information allows more accurate slot use and better alignment between planned schedules and actual operations. CDM can reduce the magnitude and duration of adjustments during irregular operations. International coordination plays a role when flights cross borders. Air traffic service units exchange flight plan data and tactical information along the route. Bilateral agreements and international standards specify how handoffs between regions occur. Over-oceanic tracks, procedural separation and position reporting are used where radar coverage is limited. Oceanic control centers publish organized track systems and monitor aircraft tracks based on filed plans and periodic position reports. Technology supports planning at multiple levels. Integrated flight planning systems combine aeronautical data, weather, fuel models, and route optimization tools. These systems can generate multiple routing options and calculate fuel and time differences among them. Decision support tools present clear comparisons for dispatchers and pilots. Electronic flight strips, data link communications, and automated coordination platforms help transmit planned timings and route choices between ground systems and air traffic control. Contingency planning is an integral part of the process. Planned schedules include allowances for delays, maintenance windows, and crew rest requirements. Alternate routings are identified. Alternate airports are designated. Fuel planning includes reserves required by regulations and operational practice. Planned buffer times in schedules help absorb small delays without disrupting connection patterns. When disruptions exceed those buffers, the systems for operational control reassign aircraft, adjust schedules, and communicate changes. At the tactical level, departure times may shift within narrow windows to manage runway capacity and traffic flow. Ground handlers and gate planners use the expected departure time to stage services. Turnaround planning considers service tasks such as refueling, catering, and cleaning. Accurate schedule information reduces idle time on the ground and improves predictability for subsequent flights. In summary, flight planning and scheduling systems are layered processes. They combine long-range timetables, route selection, performance calculations, and continuous updates. Coordination occurs among airlines, airports, and air traffic management authorities. Information flows through standardized formats and collaborative platforms. The result is a planned pattern of movements that aims to use capacity efficiently, meet regulatory requirements, and align commercial objectives with operational realities. Aircraft and control centers exchange information continuously through a set of layered communication systems. These systems combine voice, digital data links, satellite relays, and ground networks. They enable controllers and flight crews to share position, intent, clearances, weather, and traffic information on an ongoing basis. Radio voice remains a fundamental link. Aircraft crews use very high-frequency radio channels to speak with local towers, approach and departure control, and en route centers. Standard phraseology is used in these spoken exchanges. Messages are short. They include clearances, readbacks, acknowledgements, and short updates about position or intent. Voice radio is immediate. It allows the exchange of unplanned or time-sensitive information. It is also used when data links are not available or when a verbal clarification is required. Digital data links operate alongside voice. Controller-pilot data link communications, known as CPDLC, allows controllers to send structured text messages to pilots. Pilots receive these messages on cockpit displays and respond with predefined replies or with short typed responses. CPDLC reduces the need for lengthy voice transmissions on congested frequencies. It is used especially in areas where long stretches of communication are needed without constant voice monitoring. The messages include clearances, route revisions, altitude changes, and requests for information. Automatic systems also transmit surveillance and position data. Automatic Dependent Surveillance Broadcast, or ADS-B, is a continuous broadcast from aircraft that includes position, altitude, speed, and identification. Ground stations and other aircraft can receive these broadcasts. In some regions, ADS-B data is integrated into controller displays. Where direct broadcast is not possible, aircraft may use ADS-C or contract-based surveillance. ADS-C sends periodic position reports and event reports to a ground system according to a pre-established contract. These reports are adjusted to fit the airspace and the operation in question. Satellite communications extend the reach of data and voice beyond the line of sight. SATCOM links carry voice, CPDLC messages, and other flight operational data. They are heavily used on oceanic routes and in remote regions. Satellite systems provide a continuous path when ground stations are unavailable. They also support data services for airlines that are not directly part of air traffic control. These services include flight operations, messaging, and real-time weather updates. Several ground networks interconnect control centers and support message routing. The Aeronautical Fixed Telecommunications Network and its modern successor, the Aeronautical Message Handling System, carry formatted messages between facilities. These messages include flight plans, coordination messages, and meteorological data. Flight data processors at control centers receive, format, and distribute incoming messages. This distributed network allows a clearance issued in one center to be known by adjacent centers as handoffs occur. Many systems are designed with redundancy and layered pathways. A clearance can be transmitted by voice, by CPDLC, and recorded in the flight plan exchange. Surveillance data may arrive from primary radar, secondary radar transponder replies, ADS-B, and multilateration. If one path becomes unavailable, alternate paths remain. Redundancy reduces interruptions in the continuous flow of information. It also provides multiple confirmations for critical instructions. Coordination between control units depends on predictable handoff procedures. An aircraft moving from one sector or region triggers a transfer of communications and a transfer of surveillance responsibility. Controllers use standardized handoff messages to pass position, cleared level, and any constraint relevant to the next unit. These handoff procedures are supported by data exchanges across ground networks. They ensure that the next controller has current information before assuming communication responsibility. Meteorological and aeronautical information is part of the continuous exchange. Automatic terminal information service broadcasts and digital weather data feed into both cockpit displays and controller workstations. Updates to wind, visibility, cloud layers, and significant weather are distributed at regular intervals and on request. These updates can result in immediate changes to clearances or routing. Weather products are also routed through the same messaging networks that handle flight plans and coordination messages. Operational communications include routine and contingency exchanges. Routine exchanges include departure clearances, route amendments, altitude constraints, and standard traffic advisories. Contingency exchanges include reroutes, altitude deviations, or diversions prompted by weather or system limitations. The communication systems are structured to permit both scheduled and unscheduled messages. Priority handling exists for urgent messages, so they can be transmitted and acted upon without undue delay. Surveillance feeds are merged in control centers to provide a coherent picture. Radar tracks, ADS-B feeds, and flight plan trajectories are correlated. The merged picture supports decision-making and informs clearances. When surveillance data changes, controllers can issue updated instructions. Aircraft systems also receive updates. Cockpit displays use the combination of their own navigation systems and external surveillance data to present a consistent view of traffic and route status. Airlines and operational control centers also participate in the information flow. Airlines receive position reports, estimated times of arrival, and fuel state messages. They may send operational messages concerning maintenance, crew changes, or passenger needs. These messages do not replace air traffic clearances, but they provide additional context that can influence operational decisions and the timing of requests. Security and integrity of the messages are maintained through standardized protocols and validation procedures. Message formats and operational procedures are internationally agreed. These standards ensure that a clearance issued in one country is understood and accepted in another. Validation and checks reduce the chance of misinterpretation. The systems log messages for later review. These logs support routine audits and incident investigations. The combined effect of these systems is a continuous, multi-path exchange of information. Voice channels provide immediacy. Data links provide structured, efficient messaging. Surveillance broadcasts provide position and intent. Ground and satellite paths carry messages over long distances. Together, they form an interconnected framework that allows aircraft and control centers to maintain situational awareness and operational control over extended periods. The pace of communication varies with phase of flight. Near terminals, exchanges are frequent and short. In en route phases, exchanges may be less frequent but involve longer range coordination. Over remote regions, periodic automated reports replace constant voice contact. The systems adapt to the operational context while maintaining continuity in the flow of information. This continuous exchange supports routine traffic management and the fluid transfer of aircraft between units. It also provides a record of activity and a foundation for automated decision aids. The overall structure emphasizes clarity, redundancy, and standardized procedures to keep information moving between aircraft and the network of control centers. Air traffic flow management adjusts the number of aircraft moving through portions of airspace and at airports to maintain required spacing. The process balances demand with available capacity. Demand refers to the number of flights that intend to use a route, sector, or runway during a given period. Capacity refers to the maximum number of movements that can be handled without violating separation standards or operational limits. Flow management operates at strategic and tactical levels. Strategic measures are planned hours to days in advance. Tactical measures are applied in real time or on short notice. Strategic planning uses traffic forecasts and known constraints. Known constraints include runway availability, sector staffing, planned closures, and long-range weather forecasts. Tactical control responds to immediate conditions. Immediate conditions include sudden weather changes, unplanned runway closures, equipment outages, or traffic surges. A common metric used to control density is miles in trail. Miles in trail limits specify the required horizontal spacing between aircraft on the same route. A miles in trail restriction might require a fixed distance or a number of aircraft to be separated by defined intervals. Another metric is time-based spacing. Time-based spacing prescribes elapsed time between aircraft crossing a particular point. Both distance and time metrics are tools to maintain required separation based on the navigation and surveillance capabilities available. Airport arrival rates are another key parameter. Arrival rate expresses how many aircraft can land at a runway or set of runways during a fixed interval. Arrival rates vary with wind, visibility, runway configuration, and aircraft mix. Airports publish acceptance rates or runway throughput values. Flow managers compare projected demand with these rates. When demand exceeds acceptance rates, flow regulation measures are applied to reduce density upstream. Ground delay programs and ground stops are tools used to manage flow into constrained airports. A ground delay program assigns planned departure times, or delay values to flights destined for a constrained airport. The program is applied at an origin or at multiple origins to smooth arrival demand over time. Ground stops halt departures to the affected airport temporarily. Ground measures act before aircraft enter the airspace where congestion could occur. They reduce airborne holding and preserve slots within the arrival stream. Airborne measures are used when ground options are insufficient or unavailable. Standard airborne measures include holding patterns, vectoring to longer routes, and speed adjustments. Holding patterns place aircraft on racetrack-shaped tracks at fixed points or fixes. Vectoring assigns course deviations to increase route length and time. Speed control adjusts cruise or descent speeds to increase or decrease time between aircraft. Airborne measures change density within a sector while aircraft are already en route. Traffic management initiatives are coordinated actions that combine measures. Examples include reroutes that divert traffic around constraints, miles in trail restrictions on specific fixes, and slot allocations to manage flow through congested airspace. Flow managers publish these initiatives to operational stakeholders. Airlines, dispatch centers, airport operators, and controllers receive the information. Coordination allows planning of departures, fuel loads, and crew timing to match the regulated flow. Collaborative decision-making frameworks support the exchange of information. In these frameworks, flow managers share constraints and proposed measures. Airlines and airports share intent and operational limitations. The shared information improves predictability. Predictability reduces the need for last-minute tactical changes. It also allows more efficient use of ground delay versus airborne holding options. Separation minima are central to spacing standards. Minimum separation distances or times are determined by radar performance, surveillance coverage, and aircraft characteristics. Wake turbulence separation is a specific constraint. Heavier aircraft produce wake turbulence that requires greater spacing behind them. Airspace designers and flow managers consider wake categories when setting arrival sequencing and runway throughput. Reduced vertical or lateral separation minima are possible where surveillance and navigation capabilities allow. These reductions can increase capacity while maintaining the prescribed minima. Technological tools assist in managing flow. Time-based flow management systems calculate target times for aircraft at specific points. These systems consider winds, aircraft performance, and current traffic to assign metering times. Decision support tools present projected traffic density, sector loads, and predicted points of congestion. Surveillance systems, including radar and satellite-based tracking, provide position updates that inform spacing decisions. Data links and digital routing messages enable automatic updates of metering times and constraints. Weather is a frequent driver of flow control. Reduced visibility, low ceiling, convective activity, and crosswinds affect runway operation and route availability. Weather can reduce acceptance rates or close runways entirely. Flow managers use meteorological forecasts to plan measures proactively. Short-term updates to forecasts trigger tactical adjustments. The interaction between weather and traffic density explains why flow management combines both forward planning and real-time response. Slot allocation and sequencing at busy airports are methods for controlling local density. A slot is a permission to operate within a specified time window. Slots distribute demand across available capacity periods. At times of constraint, slots are redistributed or reallocated. Sequencing aligns arrival times to maintain separation and to optimize runway use. Arrival management tools create sequences that respect both separation minima and airline schedules. Network-level flow control manages the interaction of multiple constrained points. When several airports or sectors are affected, network managers coordinate measures across regions. They may reassign traffic to different flows, implement cross-border restrictions, or harmonize arrival rates across adjacent facilities. This network perspective reduces bottlenecks that arise from local measures applied in isolation. Performance monitoring supports adjustments. Flow managers monitor metrics such as airborne delay, ground delay, and average sector load. When monitoring shows persistent build-up, measures are revised. If monitoring shows excess capacity, measures may be relaxed to reduce unnecessary delay. Continuous assessment maintains alignment between planned constraints and observed conditions. Human judgment remains part of the system. Flow managers interpret model outputs, forecast information, and operational reports. They decide when to issue flow initiatives and which measures to apply. Controllers implement tactical spacing and provide feedback. Airlines respond with operational adjustments. The interaction among these roles produces a coordinated approach to managing traffic density. In summary, flow management and congestion control consist of tools, metrics, and procedures that adjust traffic density. Strategic planning anticipates demand and allocates capacity. Tactical control responds to immediate conditions with airborne or ground measures. Technological systems provide data and timing that guide decisions. Coordination among stakeholders distributes the effects of measures across the network. The result is an operational framework that maintains required spacing while managing throughput and delay. Long-term coordination, redundancy, and maintenance form the continuing framework that keeps air traffic moving across regions and time zones. Air traffic systems are composed of many parts. Those parts include human operators, technical equipment, communications networks, and procedural rules. Over time, each part is managed so that interruptions are rare and recoveries are orderly. This chapter describes how coordination, redundancy, and maintenance operate together to support uninterrupted flow. Coordination occurs at multiple levels. International standards are developed through organizations such as the International Civil Aviation Organization, often abbreviated as ICAO. These standards set common procedures for communications, navigation, surveillance, and airspace design. Regional bodies translate standards into local practices. National authorities adopt regulations and assign responsibilities. Airlines, airports, and air navigation service providers align schedules and operations within these regulatory frameworks. Coordination meetings, planning cycles, and formal agreements occur on weekly, monthly, and yearly cadences. Long-term planning addresses projected traffic growth, changes in technology, and infrastructure investments. Traffic flow management is one of the coordinating activities that operates continuously. It balances demand for airspace with available capacity. When demand approaches capacity, planned measures are applied. Slot allocations at airports distribute arrivals and departures. Air traffic flow measures adjust routes and times. These adjustments are coordinated between adjacent control centers and across national boundaries. Notices to airmen, known as NOTAMs, inform operators about changes in procedures, airspace restrictions, or equipment outages. NOTAMs are published in standard formats and linked to flight planning systems. That makes coordinated responses possible without ad hoc communication. Redundancy is built into equipment and networks to reduce the likelihood that a single failure will cause wide disruption. Surveillance installations often include more than one type of sensor. Primary radar, which detects objects by reflected radio waves, is frequently complemented by secondary surveillance radar, which receives transponder replies from aircraft. Automatic Dependent Surveillance Broadcast, or ADS-B, provides another layer of position reporting. Ground-based ADS-B stations are often supplemented by satellite-based reception. Overlapping coverage areas allow one sensor to cover gaps if another is taken offline. Communications redundancy follows a similar pattern. Voice communications mostly use VHF radio for low-altitude and terminal operations. HF radio is available for long-range communications over oceanic areas. Data links, such as controller-pilot data link communications or CPDLC, provide digital messaging as an alternative path. Satellite communications serve as a parallel channel where terrestrial links are insufficient. Redundancy extends to power supplies and network routing. Air traffic control centers and critical installations are equipped with uninterruptible power supplies and diesel generators. Network designs include multiple physical routes and diverse service providers. If one fiber path or one service provider experiences an outage, traffic can be rerouted through alternate paths. Central servers and databases are frequently mirrored across locations. Replication and asynchronous backups protect against data loss. Redundant human resources are also essential. Staffing plans include reserve personnel, overlapping shifts, and trained specialists who can cover multiple roles. Training prepares staff to operate in degraded modes that rely on fewer systems or manual procedures. Maintenance is scheduled and systematic. Preventive maintenance follows predefined intervals. Equipment manufacturers recommend inspection and replacement schedules. Aviation authorities require certification and documented maintenance programs for critical systems. Software updates follow staged rollouts. New code is tested in simulation and in controlled test environments before deployment in live operations. Change management procedures govern the transition from one software version to another. That minimizes unexpected behavior in operational systems. Physical asset maintenance occurs at fixed intervals and after specific usages. Radar antennas, navigation aids, and ground stations are inspected and calibrated. Antenna alignment, signal strength, and timing references are verified against standards. Instrument landing systems and other navigational aids undergo periodic flight checks. Runways and taxiways at airports have maintenance cycles for surface repairs, lighting, and marking repainting. These activities are coordinated with operators to limit impact on traffic. Discrete maintenance windows are planned during low traffic hours when possible. Where continuous operation is required, maintenance shifts are staggered and temporary equipment used. Long-term lifecycle management addresses obsolescence. Electronic components and legacy systems may continue to function for decades, but replacement is inevitable. Asset registers document expected lifetimes, replacement costs, and procurement timelines. Procurement processes include interoperability testing to confirm integration with existing systems. Certification authorities assess new equipment and software. test beds and pilot projects validate new capabilities at limited scale before broader adoption. Security and resilience planning are integral to maintenance and coordination. Cybersecurity measures protect networked systems from unauthorized access and disruption. Regular vulnerability assessments and patch management are part of operational maintenance. Incident response plans define roles, escalation paths, and recovery procedures. Exercises and drills test both technical recovery and organizational response. Those exercises often simulate partial outages, degraded communications, or shifted traffic flows. Results from exercises are reviewed and used to refine contingency plans and update procedures. Performance monitoring provides feedback for continuous improvement. Key performance indicators measure system uptime, delay minutes, communications availability, and surveillance coverage. Data is collected from sensors, logs, and operational reports. Trends are analyzed to identify aging equipment, recurrent faults, or procedural bottlenecks. Maintenance cycles and upgrade plans are adjusted based on empirical performance data. Safety management systems, configured for operational reliability and risk mitigation, require reporting of incidents and near misses. That reporting contributes to a knowledge base for preventive measures. Cross-border coordination is supported by formal and informal communication channels. Liaison officers, inter-agency working groups, and data-sharing agreements allow neighboring regions to coordinate route changes and capacity adjustments. Airspace redesigns are undertaken through long-term study and stakeholder consultation. Changes to airway structure, sector boundaries, and routing require modeling of traffic patterns and projected impacts. Incremental implementation and trial periods reduce operational disruption while allowing evaluation. Financial and human resource planning underpins long-term maintenance. Budget cycles fund capital expenditures for major replacements and incremental spending for repairs. Training budgets provide for recurrent skills development and simulator time. Succession planning addresses retirements and evolving competencies required by new technologies. Workforce planning aligns staffing levels with projected traffic, demand, and anticipated system complexity. In combination, coordination, redundancy, and maintenance form an interdependent system. Coordination arranges the timing and rules for movement. Redundancy provides alternative paths for information and power. Maintenance keeps components within operational parameters. Together, they allow air traffic to continue flowing over long stretches of time, with predictable procedures for handling changes and disruptions. This structure evolves as technology and traffic patterns change. Planned reviews and updates take place on regular schedules, preserving continuity while accommodating innovation.